Let us now study the input impedance of a buck-boost converter and see how we can regulate the input impedance of the buck-boost converter through duty cycle control, and let us see its effect on the IV characteristic of the PV panel from the point of view of maximum power point tracking. Let us draw the buck-boost converter interface to the PV panel. So this is the PV module. To this PV module, let us interface a buck-boost converter. The circuit of the buck-boost converter is like this. There is a BJT power semiconductor switch. Again, as I say, the BJT can be replaced with a MOSFET or IGBT. And in series, you have the inductor. You have a diode connected in this fashion, a capacitor connected like this, and this forms the buck-boost converter. To the terminals of the buck-boost converter, you have the load connected like this. So this is R0. In the buck-boost converter, the voltage is reversed. This is positive with respect to the other terminal, the upper terminal. So the bottom terminal is positive like this, and therefore V0 is positive if measured in this fashion, and I0 flows up as shown here. So this is the character of the buck-boost converter. It does give you an inversion in the voltage polarity. So that is C, D, L, Q, and across the terminals, like in the buck converter, connecting a capacitance CT like this is compulsory, is mandatory, because of the switch present here on the input line. The current through this is switched. The current is not continuous, and therefore the current through the PV panel also would not be continuous if you do not put the capacitor. And along similar arguments that we made for the buck converter, we need to put a capacitor here so that the current here from the panel is smooth and continuous, and you can effectively take peak power from the panel at every instant of time. So we will call this as VT, the voltage across the input terminal. The input impedance RT is as seen from the PV side, from the PV panel side into the terminals. It is like this. Now this current here flowing into the collector of the BJT is called IT. The current here will be called IT average, like in the buck converter. The current through the capacitance, the buffering current, will be the ICT current that will be flowing through this. This will have an average 0, this will have an average, and this will be the switched current. Let us now have the waveform axis. So axis 1 will be VL, axis 2 is IL. The voltage across the inductor and the current through the inductor, which we need. We will have another axis to indicate the current IT, which is going through the switch. And we will also see the current through the capacitor, and also look at the reason why it becomes evident that we need to put the capacitor here so that we have an IT average flowing out of the PV panel. Now let us partition these waveform time axis into various time zones like this, and mark this first time zone as DTS, 1 minus DTS. D is the duty cycle, D is taking a value between 0 and 1. This is one switching cycle, one switching period, TS. second switching period dts, and 1 minus dts. So during dts, we are keeping the BJT Q here on, so we'll say that is on. During 1 minus dts, Q is off, and so on. dts it is on, 1 minus dts it is off. Let us consider the period dts during the time when Q is on. When Q is on, you will see that there is a flow path for the current in this route. Not only that, there is a current flow here. The capacitor is discharging through the load. So the capacitor will discharge through the load in this fashion. So you will see that this potential is at minus V0. Observe that the polarity is negative, as I told you. This potential is minus V0. This potential is plus Vt. Because Q is on, this potential and this potential will be same. It will be plus Vt. This is minus V0. This is reverse bias. So this is out of the picture. So you have one circuit here with the capacitor discharging in this fashion. We have one circuit here with the current flowing through the inductor in this fashion. Let us now write down the waveform during this period. So let us first look at the voltage across L. So we will mark this VL with the polarity of measurement in this fashion. The common point of the probe is kept in this terminal, and the measuring point is kept on this side, as indicated by the arrow. So across VL, at that point in time, when Q is on, this potential is same as this potential. It is Vt. Diode is off, out of the picture. This is at ground potential, so the voltage across the inductor is Vt. So that's why we are going to draw a line like that, constant Vt, and this is what is going to appear across L. And the current through L, using that VL is equal to L dIL by dt. IL is an integral of the voltage here, so it will rise linearly, and this is IL. As IL is same as the current through the BJT, current through the power switch, IT is going to be a replica of IL. We will look at ICT much later. Let us finish the periodic cycle waveform of all these three parameters, and then later we will look at ICT. Now let's see what happens during 1 minus dts time period, and this is the time period when Q is off. When Q is off, IT is 0. There is inductor current, but the inductor current will continue to freewheel by making this diode on, so it will freewheel in this path. And let us draw that path. So the inductor current will freewheel in this path, with a part of it going through the load R0 and another part going through the capacitance to charge it up in this fashion. Now let us draw the waveforms for this part of the circuit during the period 1 minus d into Ts. So if you look at the voltage across the inductor, you see that Q is off, the diode is on. This is V0 voltage with this negative, so you have minus V0 coming across the inductor, so that is V0. And this is negative portion, this is the positive portion. Negative and positive portion should balance out so that the average is 0. So for the inductor current, during the on time, we saw that the inductor current was rising up, inductor was charging with a slope of Vt by L. It will now discharge with a slope of minus V0 by L. So it will discharge like this. IT will be 0 because Q is off, there is no IT current, so this will remain 0. Now for the next cycle also, the same thing will repeat. Let me quickly write that down. So that would be for VL, IL and IT. Before we get to the input-output relationship between RT and R0, we need to do some analysis on these waveforms, because we need some intermediate relationship which we will be using for finding the input-output resistance relationship, because we need to know what is IT average and few other parameters. Now consider the current that is flowing through this branch or the diode branch, one of these. So let me mark it there. And if you look at the inductor current waveform, observe that the inductor current, while the transistor Q is on, the inductor current goes in this direction, and while it is off, the inductor current goes in this direction. So which means this current here is contained within the inductor current waveform as shown hashed in this fashion here. So that would be, this portion would be the portion of the waveform that you will find if you probe here. Now that is actually composed of IC current and I0 current. So therefore it is I0 plus IC. I0 is the DC component, an average component of the current. IC does not have an average component, so it is a component of the current here, which is an AC component without average. So approximately I0 would look like this, plus IC would look something like this. This hashed portion of the current contributes an average value here of value I0. Here too there will be an average value. That average value will be IT average. So therefore the average value of the inductor current will be IT average as contributed by this portion, and I0 as contributed by this. So this will be IT average plus I0. Now consider IT, the current through the BJT. So this value, this line that I have drawn here is the average value of the switched IT waveform, and that we have called it as IT average, and that is what we expect to flow here, the IT average. This is the switched IT, and the buffer current is through CT, the ICT. So let me draw the inductor average current like this. So as we argued just before, this portion is, this line is a contribution of the average during dt and contribution of the average during 1 minus dt. So therefore we have inductor current average as IT average plus I0. The value, this line, the average inductor current line is given by this relationship. So knowing that this value here cutting across through this linearly increasing IL waveform is IT average plus I0, and as IT during the dt portion is same as the inductor current, we can say that the value that cuts across in between the linearly rising portion of the IT waveform will be IT average plus I0. So if you mark those average value, you will see that that will be same as IT average plus I naught, both here and here, same value as this. So if I take this dotted black line every cycle, that would give me a flat topped rectangular wave shape. Let me redraw that down here, and it will appear something like this. And this has a flat top value of IT plus I naught, as I've indicated here, this portion and this portion, and there is an average value IT average. Now this we can write it as IT average is actually this peak value into D duty cycle. IT average plus I naught into D will give you the average value IT average. So if you simplify, you will get IT average, which is equal to I naught into D by 1 minus D. So this is an important relationship we need, because this is the value IT average in terms of I naught and D. We need to know what is the value of the current, the continuous current that is flowing out of the PV panel source. From here, it is easy to deduce the current flowing through CT, ICT. So you see, this is average, IT average. So if we make that as a zero line, the current through the CT is obtained directly from here. So the portion above the IT average line is the charging component, and the portion below the discharging component, and so on. It repeats cycle by cycle. So this portion, if we write it down separately here, that portion like that, you will see that ICT will have a wave shape something like this. So during the DTS period, there is current flowing through Q. The average component, the DC component, is coming from IT average. The excess varying component is provided by CT. And during the 1 minus DTS time, when Q is off, IT is 0. So all the IT average component is going into the CT capacitor that is charging it up. Now we are ready to find out the voltage, current and resistance relationships. Let us write down the voltage relationship, input-output voltage relationship. We look at the inductor current waveform. We know that we need to have a balance between the positive part and the negative part. So within a cycle, the positive part should balance out the negative part. So Vt into dTs, Vt into dTs plus minus V naught into 1 minus dTs should be equal to 0. This implies that V naught is equal to Vt d by 1 minus d. Remember that we have chosen the measurement of V naught itself reverse. If we have chosen it in a regular sense, we would have got a minus sign here. This minus sign would not have been there. So therefore, V naught is equal to Vt d by 1 minus d is the input-output voltage relationship of this converter. Now the current relationship we have already seen. IT average, we need IT average and I naught. IT average is related to I naught in this following manner: d by 1 minus d, we just now saw through this waveform. Or I will write I naught is equal to IT average 1 minus d by d. So this is the second relationship. The resistance relationship is obtained by the relationship 1 divided by 2, which will give you R naught, which is equal to V naught by I naught, which is equal to Vt by IT average into d by 1 minus d whole square. Vt by It average is nothing but RT as seen from the input terminals, the terminals of the PV module. So therefore RT is equal to R naught, this will come this side, 1 minus d by d whole square. So this is the input output resistance relationship for the buck boost converter, and we need to see how this affects the IV characteristic of the PV module and what is the takeaway that we can get out of this particular relationship for the maximum power point tracking problem. Now let us draw the IV characteristic for the case of the buck boost converter interfacing the PV module. So let us draw the graph. So you have the x-axis Vt, the terminal voltage across the panel. The y-axis is It average. Let me draw the IV curve in blue. In green you have the power versus V curve, and I have a load line here 1 by RT, and at the point of the intersection we have this operating point, and when you drop it down, it drops down to the power curve, and that is PM, the maximum power. So this is a maximum power operating point. Now for the buck boost converter interfacing the PV module, RT is equal to R naught into 1 minus d by d whole square. So this is the relationship that we just now obtained. Now let us see what happens at d is equal to 0. So when d is equal to 0, whatever may be the value of R naught, this works out to be infinity. So RT will be infinity, which means that it presents an open circuit to the PV panel. So the load line, the virtual effective load line, is along the x-axis. So let us draw that. So here you have 1 by RT at d is equal to 0. Now if d is equal to 1, this is 1, this will be 1, and this is 0. So whatever may be the value of R naught, this works out to be 0. So RT is 0, implying that it is presenting a effective short circuit across the terminals of the PV panel. So which means it is along the y-axis. So let us draw that and then mark it 1 by RT at d is equal to 1. So as d progresses from 0 here, the load line from a horizontal value starts moving to a load line which is vertical, which is having infinite slope at d is equal to 1. So this means that all the points of the IV curve in the first quadrant are reachable by the buck boost converter. So this entire first quadrant portion of the IV characteristic are possible operating points for the PV module, and therefore obviously the peak power point will definitely come within the range of the buck boost converter. So one of the main advantage of the buck boost converter is that it covers the entire first quadrant, and any point on the IV characteristic is reachable by the buck boost converter interface. So this is the important takeaway. Entire first quadrant is the range of this converter. So for maximum power point tracking, from the point of view of maximum power point tracking, this would be an universal converter where any point can be reached for any insulation and any type of load.